So this is common drain. Let's now look at common source. So for common source, I'll consider a signal source resistance Rs to demonstrate a point. So this is what you have, and the output is taken from the drain here, and let's say have a PMOS transistor as the current source connected like this. So once again, let's lump all the capacitors. So from the gate, I'll have a bunch of capacitors to ground. I'll call that C1. Similarly, from the output node, I'll have a bunch of capacitors connected to ground. I'll call it C2. And between these two nodes, I'll have the CGD. Correct? To start with, I'll not consider this capacitor, and then we'll see later. Right? So as of now, I'll consider only these two capacitors. So I basically, yeah, okay. So now let's find the zero locations. So this is the zero. So how many zeros I have in the circuit? How will you find it? Let us say I short C2 to ground. What happens to the output? So there is no zero here. If I short C1 to ground, what is the output? Non-zero or zero? Yeah, I mean I short the gate to ground. VGS of the transistor is 0. No current flows through M1. What will be output? 0. So which means how many zeros I have here? Huh? Yeah, 0 zeros. Perfect. Let's now look at the pole. So again, for pole locations, the input is irrelevant. So I'll short the input. So this is what I'll have. So how many poles I have here? 2 poles. I can initialize both capacitor voltages independently without any contradiction. Now tell me if these two capacitors, have second order system. Once again, I can write the pole as 1 by R times C. Under what conditions? If they are uncoupled. So let's check if it's uncoupled. Do you think, let us say the resistance seen by C1, do you think it will change if I short or open C2? Yes, why? It will not change, because remember, looking here is gate. This is basically isolating both capacitors. Right? So which means the resistance seen by C1, how much will that be? Resistance seen by C1 is going to be Rs. That's not going to change based on whether C2 is open or short. Similarly, what can you say about the resistance seen by C2? What is the resistance looking here? Looking up, what is the resistance looking up? 1 upon Gm or R0? Looking into the drain, so it is R0 of M2. Looking down, it is, that will also not change whether I open or short C1. Okay. So which means this is essentially R01 parallel to R02. So which means the poles are uncoupled. So I can directly write one pole as 1 by C1 times Rs. I will write it as GS by C1, where GS is basically 1 by Rs. Similarly, my second pole is exactly at 1 by C2 times the R01 parallel to R02. So this I will write as an output conductance G out by C2. This is fine. Here the poles are uncoupled, so it's trivial. Again, remember here I didn't consider the effect of the gate to drain capacitor, so life was simple. Of course, life cannot be that simple, so let's make it hard. So let's include the effect of CGD. Okay. So now we'll consider the capacitor CGD. I'll call it as C. In general, remember the CGD capacitor is typically much smaller than the gate to source capacitor, but in this case I'll assume that I'm going and putting an explicit capacitor C. Okay. In addition to CGD, let us say you put an additional capacitor across it. So now tell me, if I have zeros in the circuit here, which capacitor you can short and the output is still non-zero? Can I short C2 to ground and output is non-zero? Output is 0. If I short C1, what happens to the output? Output is still 0 because gate to source is 0 if you short this. What about C? If I short this capacitor C, output is non-zero. So how many zeros I have? Right? Can I have 2 zeros here? If I short any two capacitors, the output will be 0. So I cannot have 2 zeros, I just have 1 zero. Again, now let's understand the physical origin of the zero. So at the output I have two different currents getting added up or two different voltages getting added up. Yeah, I have two different currents from the input to the output. What are the paths for the current? One is through this, other is through the transistor. Okay. Let's calculate the location of 0. How will you calculate the location of 0? Yeah, we'll assume that V out of S is equal to 0 and then apply KCL and try to solve for the circuit. So let us say this is this node is 0. Let me call this node voltage as some V1. Let us say this is some V1 of S. So help me write KCL at the output node. What is the current flowing? Let's write the current this direction. What is the current flowing through the transistor in this direction? Very good. Minus GM1 times V1 of S. What is the current flowing through the capacitor in this direction? This potential is V1. This is 0. V1 of S times. So sum of these two currents must be equal to what? I mean, sum of these two currents must be equal to what? 0, because this node voltage is 0, so current flowing through M2 is 0. Similarly, current flowing through C2 is. So once again, I know for a fact V1 of S is non-zero because I am applying some non-zero input. So I'll obviously have some non-zero V1 of S. So what is the value of S now? Is plus GM1 by C. So do you think the 0 is in the left half of S plane or right half of S plane? Right half of S plane, right? So that is something to remark. This is an RHP 0. Again, that happened because the currents flowing through the capacitor and the transistor here, they have different signs. Correct? So if both were plus here, you would have gotten an LHP 0. So in this case, both are minus, so it's an RHP 0. So this is another observation you can make looking at the circuit, right? Whether the 0 will be in the LHP or RHP. So we have found the 0. So let's do the poles. So I am considering this capacitor C. Okay, so now tell me if the, first of all, how many poles I have here? 2 poles. Why? if I let us say initialize the voltage across C1 and C2, the voltage across C is automatically determined. You don't have independent control to initialize this capacitor voltage. So I have two poles, that much is clear. And do you think earlier, remember, without this C, these two capacitors were uncoupled. Now I have added this capacitor C between them. Do you think they'll be coupled now or uncoupled? They'll be coupled because you are going and putting this fellow and connecting these two. So you'll have a strong coupling between the two capacitors. So you cannot make direct, guesses saying that pole is 1 by C times R. So there is no other escape. You have to actually go and solve for the circuit. So let's say this is your input, this is your output. You apply KCL here. How many nodes you have in the circuit? How many nodes are there here? I have one node. So I have two nodes and I have two unknown voltages. One is V out, other is this gate voltage V1. So you write two KCL equations. So you have two unknowns, which is V1 and V out. So you'll get a simultaneous equations like this. You can solve it using any of your favorite method, right? And I say my life is too short for me to do algebra in classes like this, but you guys are younger than me, so you have a lot of time. So you go back, write KCL and try to solve for it. I'm hoping you can solve simultaneous equations because everyone has passed your 12th standard. And if you do this, this is a transfer function you get. I mean, you don't have to copy this. This is not relevant. I'll tell you what you might want to copy later. So this is what the transfer function is. As expected, we have an RHP0 at GM1 by C. That is something we calculated now. To find the pole locations, I have to find the roots of this polynomial. So a quadratic equation. You know the roots of a quadratic equation? Minus b plus or minus root of blah blah blah. You put it, you will get each pole to be 3 lines long. So as I say, the mathematician in you should feel excited, but the engineer in you should feel really ashamed, because we are not here to derive pleasure from looking long equations, right? So as engineers, how you might go about solving this? Yeah, what did I say? Sorry. I mean, forget about C1, C2. I give a second order polynomial equation. What is the approximate way to solve for this? Yeah, we'll assume that roots are far apart. Let us say assume that one of the poles is much smaller than the other. Then how can you approximate the poles as? I mean, we already saw in the last class, right? If I have very low frequencies, which terms here will dominate? The 1 plus s term. So you can approximate the polynomial as this. So the low frequency pole will be the ratio of these two coefficients. At high frequencies, these two terms will dominate. Take the ratios of these two. That will give the high frequency pole. Fine. Again, I did that, and if you do this, this is what you will get. Again, you don't have to copy this also. I'll tell you what to do. But a normal engineer makes his assumptions, get the pole locations, and he or she will stop there. But what will a good engineer do? Yeah, you have to go back and verify if the assumption is valid. Let's check it. And for the for example, let's assume that my conductances and the capacitor, all the conductances are of similar order, and I'll assume all the capacitors C, C1, C2, they are all of same value. Let's look at the denominator here. So the denominator, I have C into 1 plus GM R0, right? GM R0 is the gain of the common source amplifier. So here I have C into gain of the transistor. Here I have just C. So which of the two denominators will be larger? P1's denominator of P1 will be larger or P2 will be larger? P1, because here I have a capacitance multiplied by a gain. Let's look at the numerator. For P1 I have a conductance. For P2 also I have conductances, but I also have a GM term. And remember, my GM times R0 is much greater than 1, or GM is much greater than G0. So which of the two numerators is greater? This is GM is much greater than G0 and GS. So which means P2's numerator is greater. So I see that denominator of this fellow is larger, numerator of this fellow is larger. So what is at a lower frequency? So which means I know P1 is much smaller than P2. Assumption is fine. Okay. Now a good engineer stops here. A smart engineer will try to understand why these results make sense. Of course, I want you guys to become smart, so I'll try to give a motivation as to why these make sense. And before that, let me quickly summarize the result, right? So let me draw the circuit once. So this is the common source we considered. So this is the transistor. For small signals, how can you replace the transistor as? Voltage control. So I'll replace it with an OTA, this symbol. Okay. I'll let you figure out why I mark this as minus and why this as plus. Take it as an exercise and try to argue. And this is my RS. So this is my output. At the output I had, let us say, an equivalent output resistance. So let us say that is some R0. And I consider two capacitors. Correct. And I had a capacitance from gate to drain. So basically what I'm saying is this is your gate terminal, source and drain. Now when I didn't have the capacitor C, correct, let me first do that. So without the capacitor C, can you tell me the pole locations? I mean, without the capacitor C, here I have two RC sections. Are they coupled or uncoupled? So what are the pole locations? Yeah, I'll say GS by C1, G0 by C2. Right? So now I included the CGD or the capacitance from the input to the output. And I got some long things for poles. Let me just copy paste it. Don't have to copy this for now, don't worry. Let's quickly try to see why the pole locations here make sense. Let's start with the low frequency pole. And for that I want to take a small digression. So let us say you have a voltage amplifier with a gain of -8. If I mark it like this, what kind of a control source I am talking about? Voltage control. So let us say I put some impedance, so it can be anything. Let us say a capacitor. If I put this and let us say I try to find the equivalent resistance looking here. How will you find the equivalent resistance? Not the resistance, equivalent impedance here. How will you find it? You apply a test voltage, find the test current. So let us say this is VT. Okay. So if so, what can you say about this voltage? A times VT or something else? So which means what can you say about the current through the capacitor? That is my test current. How much will be that? I have VT plus AVT times. So this I can write as VT of S into 1 plus A times. So which means, I mean, some of you might know this already. So which means looking here, it seems like I have a capacitance with a value of, this is an effective capacitance whose value is 1 plus A times C. So I can basically redraw the setup like this. So I know that the looking in resistance or looking in impedance is an effective capacitance with a value 1 plus AC. So I'll mark it like this. When I say the looking in impedance, it is essentially the impedance from that node to ground, correct? That's what I marked. And this is referred to as Miller effect. Now you can argue the other way also, that is, let us say if I call this voltage as Vx, what should be this voltage? Minus Vx by A. So once again, if I have, let us say, this fellow here, so the current flowing here will be Vx times 1 plus 1 by A times Sc, correct? So which means you can argue that from the output side it looks like I have a capacitance of value 1 plus 1 by 8 times C. That is basically the impedance I am looking from here. But this result is not really relevant because I am putting this at the output of an ideal VCVS, correct? So it doesn't matter what is the impedance I put, the result is going to be same. So when you have a VCVS, you know, the output side result is not really relevant, but what is relevant is the input side impedance. So the bottom line, anytime you have a voltage amplifier or a voltage controlled voltage source, you have an impedance put across it, the looking in impedance is going to look like this. And at the output side it is not relevant because we are dealing with a voltage controlled voltage source, so it doesn't matter what you put at the output end. So this is, let us say we know this effect now, and this Miller effect we saw is in context of with respect to what kind of a control source? Voltage control. But now let's say I have this fellow, let me copy this. So this is the setup I have. Here what kind of a control source I have? So voltage control, right? Now in a voltage controlled current source, at the output what quantity is fixed, the voltage or the current? So here the only quantity that is fixed is the current. So which means the voltage here will depend on the impedance connected at the output. So I have a fixed current flowing, and this current has to flow through the effective load connected here, and that's what will generate the voltage, right? Now remember, if I were to use the Miller effect, I need to know the exact voltage gain from this node to this node. Now if this is a voltage controlled voltage source, that gain is constant, which is minus A across all frequencies. Now I have a voltage controlled current source. So is the voltage gain from this node to this node constant all across frequencies? Because the only thing that is fixed is the current here. The voltage gain is not a constant, it is actually will be some A of S, correct? So which means using Miller effect here is non-trivial because you have to exactly find what is this A of S. But of course I say as engineers we never take no for an answer. So what we do is the following. Let's assume that I look at very, very low frequencies. At very low frequencies, what can you say about the capacitors? They can be treated as an open circuit. Let me actually mark it clearly. This is from this node to the output. So which means if I redraw the VCCS alone, this is what I'll have without the capacitors. Fine. So now can you tell me the voltage gain from this node to this node? If I call this GM1, how much is the voltage gain from this node to this node? Okay, first of all, what is the current flowing here? If I call this voltage as some Vx, what is this current? Minus GM1 times Vx. So this current is minus GM1 times Vx. So this flows through. So what is the voltage gain? So here I can say that my gain is, so which means at low frequencies I can approximate that my A of S is a constant which is equal to Again, this is an assumption we are making. So which means now at low frequencies I can say I can use this Miller effect. So this is what we call as Miller approximation. Right. So we are not using Miller effect directly, because if you want to use the Miller effect exactly, you need to know the exact gain from this node to this node, and that will be a function of frequency. Instead, what we do is the following: we assume that we are working at low frequencies, wherein the gain can be approximated to be a constant, which is Gm1 R naught. So then can you use the Miller effect? So you have V in Rs C1. Now we already saw if I have a capacitor connected across a gain of A, the capacitance, equivalent capacitance is 1 plus A times C. Here what is the value of A? Gm1 R naught. So this is going to be C into, and then I have the OTA here. So the moment I do this, you see that earlier this capacitor here was coupling these two nodes, correct? Now this fellow is not coupled. So this can be treated as an isolated first order RC section. What can you say about the pole location here? What is the total capacitance I have? C1 plus C into 1 plus Gm1 R naught. The resistance is Rs. I will write as a conductance Gs. And again, remember, the assumption we made was this is a low frequency pole, and we can check it. In fact, we saw that the pole 1 we saw as a low frequency pole. Right? We saw this was actually much smaller than P2, so this is a low frequency pole. So let me actually copy the expression we got from solving the equation. So let me just hold on. So this is the expression I got from approximately solving the quadratic polynomial, and intuitively this is what we guess as the pole location. Correct. So here I have GS, I have C1, sorry, I have basically C1 plus C into 1 plus Gm R naught. I have this term also. Of course, I have a small additional term here, and that is happening because we did a Miller approximation to start with, so it is bound to happen that there may be some errors here and there. And also to start with, we even solve the quadratic equation using an approximate result that I can take the ratio of polynomials. So you have done multiple levels of approximation, so all of them can be attributed to this additional term. But in practice, the dominant term is going to be this fellow, because I have a capacitor multiplied by a gain. That is going to be the dominant thing. So for all practical purpose, you can approximate the low frequency pole as this. So we'll stop here and we'll continue and understand why the high frequency pole makes sense. Yeah. Yeah, there also if you use, see, I wanted to demonstrate Miller effect, so I introduced Rs here. Okay. Yeah, his question is, why didn't I consider Rs here? Yeah, because I wanted to simplify my life here, so I didn't consider Rs. But in the common source, I didn't want to simplify my life, so I considered Rs.